Hey everyone, this is Dr. Walker. This video is about the guided examples from 255, which was about right-hand rule number 2, and finding the magnetic field due to a straight wire. Let's take a look at the example. It says, two long parallel wires each carry a current of 5 amps. If the wires are 15 centimeters apart, find the magnetic field midway between them. And there are two different parts to this problem. So let's draw the wires. And for part A, the currents are in the same direction. So you can draw the currents going up. You can draw them going to the right. It doesn't matter, as long as you draw them in the same direction. Find the magnetic field midway between them. Okay, so what I want you to do is use the right-hand rule, number 2, to figure out what is the magnetic field direction due to wire 1. I call this the left one wire 1 and this one wire 2. What is the direction of the magnetic field at this location due to wire number 1? So use your right-hand rule and let's see if you came up with the right answer. Again, pause the video as much as you need to. You put your Put your thumb up, straight up, and see which way your fingers are curling to the right of the wire. So they're curling this way, which is counterclockwise if you are looking from above here. So do the curling with your left hand and then just stop when you get to the location that you care about. We care about a point to the right of the wire. Stop and think about, well, which way are we going? We're trying to keep going, right? We're trying to go this way. So if you stop here, you see that you're going into the page on the right side of that wire. So hopefully you're doing the same thing I'm doing. The right side of the wire, we are going into the page. Okay, now let's take a look at wire number 2. Which way is the magnetic field produced by wire number 2 on the left side of wire number 2? So do the same thing. The current is going up. When you loop around, if you are on the left side of the wire, you're coming out of the page. Remember, the page is straight in front of you, vertical. So you are going out of the page if you're looping around this way. And you stop when you're at the left of the wire. So wire 2 is producing a magnetic field out of the page at that location. It turns out that the point midway between them is the same distance from both, right? This distance is the same. So that means that the strength of the magnetic field produced by each wire is the same. If we go back to the equation, B equals mu I over 2 pi r, this gave us the field due to the straight wire. So the field depends on the strength of the current and the distance from the wire. Both wires have the same current. Both are at the same distance from this location. So they both create the same exact field. So if one field is into the page and the other field is out of the page, what's going to be the net field? Did you get that the net field is going to be 0 teslas? Right? Because the two fields cancel each other out because they're in opposite directions. Okay, so now what happens if the currents are in opposite directions? So you can draw one going up and one going down. Doesn't matter which one is which. And let's take a look now. What is the direction of the magnetic field at a point to the right of wire number 1? It's the same thing that we found before. It's going into the page, right? The current is going up. You are looping your fingers around. You are going into the page when you are to the right of that wire. So we have a current into the page, a magnetic field into the page from wire number 1. What about wire number 2? go ahead and use the right hand rule. The current is going straight down, so now which way your finger is looping? They're looping like this, which would be clockwise as viewed from above. So if you stop when you're to the left, you're going into the page, right? If you're going to the right of the wire, coming out of the page, but as you're looping to the left of the wire, you're going into the page. So wire 2 is also providing a magnetic field into the page at that halfway point. So now, since magnetic field is a vector, you know that if they're both going in the same direction, they're just going to add up. So the net field at that midway point is going to be B1 plus B2. They're going to add up. And both fields have the same magnitude because we're using mu I over 2 pi r for each one. And both have the same current and the same distance. So we can rewrite this as just 2 times mu I over 2 pi r. And then we can plug in the values where we have, which the 2's will cancel out, but we have mu, the current mu naught, which is 4 pi times 10 to the negative 7. Hopefully I'm remembering that correctly. And then the current is 5 amps. And then we're going to divide it by pi times r. And r is the distance. So it said that the wires were 15 centimeters apart. So r is that halfway point distance. That's going to be 7.5 centimeters because it's half of the total 15. The total distance here is 15. But we want to go ahead and convert the r to meters. So 0.075 meters. All right. So we're going to put that right there. 0.075. And when you plug all of these numbers in, you're going to get about 13.35. Sorry, we've already multiplied by 2. You're going to get 26.7 microteslas when you plug all of these numbers in. When you plug it into your calculator, you could, if you wanted, just cross out the pi's. They do cancel out. So hopefully that made sense. When you are talking about magnetic field, it is a vector. It does have a direction. So use right hand rule number 2 to find the direction of that magnetic field if it was a straight wire that was producing that field. See you next time.